As I mentioned in the introduction to the class, the learning objectives of Biology 3665 fall into two streams. First, I aim to introduce key concepts regarding form and function of organisms to help you understand why organisms are built the way they are. Most of these concepts relate to first principles and are the same for an inanimate structure as for an animate structure. A first principle is a basic proposition or assumption that cannot be deduced from any other proposition or assumption. For example, the pole of the gravitational field of the Earth is fundamental, irreducible, and the same for an animal or for a beam of steel. This week we begin a series of labs and lectures that introduce the study of size and shape of organisms, which is of central importance to understanding organismal form and function. The roots of this area of study run very deep, and I think are fascinating, thus I will begin by discussing some of the history of the field. I will then briefly provide some examples of how organismal design must change as body size changes, focusing largely on the material properties and strength of bone. We will continue with this theme next week. In this module, as well as next week's modules, we will be considering scaling of terrestrial or semi-aquatic organisms. However, the following week we'll turn our focus to scaling in aquatic organisms. The second stream of objectives will be to give you hands-on experience studying how size and shape change on appendicular skeletal elements from a growth series of alligators and ostriches. This week you will analyze how length, surface area, and volume change as a function of changes in body size. You will develop predictive models for your data and assess how good these models are. Next week, you will collect some additional data on the cross-sectional area of a bone and try your hand at geometric morphometrics. One of the earliest pioneers of the study of organismal form and function was Aristotle, who lived between 384 and 322 BC. He is often considered to be the father of comparative anatomy, and wrote a series of books on animal form and function. For example, in De Motu Animalium, on the movement of animals, he described animals' bodies as mechanical systems and analyzed the actions of muscles and bones using geometry. Another early pioneer that made contributions to this field is the Venerable Galileo, who is often called the father of the scientific method and the father of physics. Galileo's astronomical observations had led him to support the Copernican view that Earth revolved around the Sun and rotated on its axis, rather than Earth holding still and the Sun and other celestial bodies revolving around Earth, which landed him in hot water with Pope. He was tried by the Inquisition, found nearly guilty of heresy, and sentenced to house arrest for the remainder of his life. While under house arrest, he wrote a book titled Discourses and Mathematical Demonstrations Relating to Two New Sciences, which was published in the Netherlands, somewhat out of the long reach of the Pope, who had banned any further publications by Galileo. One of Galileo's two new sciences is now known as kinematics, the study of objects in motion, and he figured out some of the principles that we now mainly attribute to Newton, such as a body in motion will stay in motion unless acted upon by a force. The other new science is the study of the strength of materials in relation to their size and their shape and the ways in which they are loaded, or, as stated by Galileo, quote, treating of the resistance which solid bodies offer to fracture. I have put a PDF of this publication on Canvas for those who are interested in perusing it. The book deals with materials properties of both inanimate structures as well as organic forms, and is really quite a remarkable book. In the first chapter, Galileo notes, and this is again a quote of the translation, small animals are proportionately stronger than larger, and smaller plants are able to stand up better than larger. That a tall oak of 200 cubits high, which is about 300 feet, would not be able to sustain its own branches if they were distributed as in a tree of ordinary size, and that nature cannot produce a horse as large as 20 ordinary horses, or a giant 10 times taller than an ordinary man, unless by miracle, or by greatly altering the proportions of his limbs, and especially of his bones, which would have to be considerably enlarged over the ordinary. Sometimes a picture really is worth 1,000 words, and I think this slide brings home a couple of important points. The slide shows a photograph of an oak tree and an illustration of some of the tallest trees that are currently found on Earth, and these trees are drawn to scale. I have enlarged the oak tree so that it is the size of this hypothetical oak tree discussed by Galileo, 200 cubits, which is about 300 feet, which is about 91 meters. So it's on the same scale as these tallest trees. All I did was enlarge the photo so that it remained proportionately the same. So the breadth increased just as much as the height increased. Of course, oak trees don't actually grow this tall, right? So you have to realize this is just me taking the photograph and enlarging it. So the tallest tree known is a sequoia, and it's of the species Sempervirens, and the tallest individual actually has a name. It's known as Hyperion, and it's about 380 feet, so that's a little taller than the hypothetical oak. The second tallest tree is also a sequoia, of the species Giganteum, and I marked the approximate 300-foot distance or height with these two scale bars. And that's how I decided, how big to make this oak tree. So the first important point is that none of these tall trees, and these are found all over the world, one group is from Africa, Australia, etc. None of these tall trees are shaped anything like this oak. So this raises the possibility that Galileo was correct, and that there's some sort of intrinsic property in the mechanical strength of wood, so that it's just absolutely impossible for wood to form a tree that is shaped like an oak but is 300 feet tall. So the shape has to change due to these mechanical properties, or the structure of the wood would have to change. If you could build the tree of steel, then this shape is probably possible. Or if this oak tree were growing on the moon, where there's reduced gravitational pull, or in a space station, this shape, would be possible in some space colony. But given this first principle of the Earth's pull, its gravitational field, and intrinsic strength of wood, you can never, this is a constraint, it's a mechanical constraint, you can never produce a tree of this shape that's this tall. That's what Galileo would argue. So the second important point is that if we look at the distribution of these trees and the phylogeny of these trees, the family history, we know now, Galileo of course didn't, because this is all tied into the theory of evolution, which was, initially worked out by Darwin in the 1800s, and this book goes back to the 1600s, right? But we now know that these trees are not closely related. So the first two, the sequoias, are gymnosperms, and the other lineages are all angiosperms, or flowering plants. And we know the split between the gymnosperms and the angiosperms happened around 300 million years ago. And we also have a fossil record of these trees. So we know that the common ancestor of gymnosperms and angiosperms didn't look like this, right? It was like a seed fern. So we know this is an example, quite an extraordinary example of what we call convergent evolution. This is not a result, it could have been, right? It could have been just a result that these trees inherited genes from their ancestor that made them sort of spindly, tall and spindly. But we know that's not the case because we know what those common ancestors look like. And I don't know enough about plant phylogeny to go into the angiosperms, but you could go in and I would imagine the eucalyptus are not very closely related
to these other trees. And then if you found their common ancestor, they wouldn't be these tall, spindly trees either. So there's probably an example of not just one convergent evolution here, but multiple convergent evolutions. And that's one of the things that I think is so exciting about taking this approach to understanding organismal design, is that, yeah, you can have a structure, you can have a shape evolve that is simply a consequence of inheritance from an ancestor. And there's no real selection on it. It's just randomly drifting. But that is almost never the case when you're considering structures that are mechanically important, that have a real function underpinning them. And so by identifying these examples of convergent evolution, often you can sort of get down to the nitty-gritty of what the function of that structure really is. And it provides a lot of insight into radiation of groups and into evolutionary history of groups. So that's pretty exciting. Okay, so 2 important points. A, Galileo was probably right. He didn't understand exactly any of this evolutionary theory, but he was probably right that this is just what we would call a mechanical constraint. You can't do it. You could do this on the moon, but you can't. Mother Nature cannot build a tree shaped like this oak that's 300 feet tall. Because of the pull of the earth and the materials properties of the wood. And B, that this is, when we see these tall trees, we can guess and probably be right that this is an example of convergent evolution. So if we didn't have their fossil record, for example, we could still probably guess this is a functional trait that's evolving again and again and again. And it is an example of convergent evolution. This is a copy of an illustration from the book showing a sketch that Galileo made of a bone from a small animal. And he states, "I have sketched a bone whose natural length has been increased 3 times and whose thickness has been multiplied until, for a correspondingly large animal, it would perform the same function which the small bone performs for its small animal. If one wishes to maintain in a great giant the same proportions of limb as that found in an ordinary man, he must either find a harder and stronger material for making the bones, or he must admit a diminution of strength in comparison with men of medium stature. For if his height be increased inordinately, he will fall and be crushed under his own weight." Again, this underscores the idea that given intrinsic mechanical properties of bone, changes in shape are mandated with changes in size. Another reason that I really love this approach to understanding animal form and function is that it can be rigorously applied to understand life history of extinct lineages. So for example, sauropods are the largest terrestrial animals that have ever lived on Earth. They are intrinsically fascinating to me and to many other people. So if a scientist wants to ask questions about their life history and retrodict how they moved and lived, then using those first principles enables them to draw sound and probable conclusions. So one might want to know, could sauropods rear up on their hind limbs to better reach tall food items, or maybe to free their forelimbs for fighting? Or you might wonder, could they ever hop like a kangaroo, or canter, or trot, or gallop like a horse, or even walk at a rapid pace? Then it is possible to calculate from these first principles whether their limb bones could tolerate such types of locomotion. We know from looking at living animals that no bone has ever evolved that is as strong as steel, or as plastic as chewing gum. So we have a range of reasonable values to use to retrodict this history. So we can base these calculations on these material properties, these known material properties, and then go back in time in a way, travel in an imaginative journey back in time, but in a scientifically valid way to understand this life history. There are also a lot of clinical reasons to understand these structure-function relationships in terms of helping people building implants that help people and pets that are injured or when suffering debilitations from aging, for example. So why did Galileo conclude that proportions must change, or material properties of the bones or the trees must change in order for a structure to increase in size? We now know that the answer lies in the way atoms and molecules interact in solid structures when acted upon by an external force or a load. But Galileo was working before we had an understanding of the atomic theory of matter. Yet he surmised there was an interaction between microscopic properties of solids and external forces. And in this book, he spends a considerable amount of time wondering just what it is that holds the solid together, and pondering whether or not there was a sort of a vacuum that served as the bond between these smaller particles of matter. You have to remember that Galileo was an inventor and an experimentalist, as well as a mathematician and a physicist. And he didn't, for example, invent the telescope. That happened in the Netherlands, but he heard about the invention and then he made telescopes. And he taught himself how to grind the lenses and to put them together and make these instruments. And then, of course, he used these instruments to do amazing things. He discovered sunspots. He discovered 4 of the moons around Jupiter. He discovered that these moons actually pass out of view and surmise correctly. That's because they're going behind the planet, and then they pop out on the other side a little while later. And he designed other instruments, and some of them he actually built. Some of them he just put down the designs on paper. Like he designed instruments that could weigh air, for example. So he even employed an artisan, a craftsman that lived in his house to help him construct these instruments that he designed. And he knew that if you grind a hard surface and polish it, a surface such as glass or marble, and put these together, that they're very difficult to pull apart, that there's a vacuum there that are holding these solid structures together. So that's why he thought maybe there's like these mini vacuums inside of these solids that are holding small particles together in this larger structure. So in this book, he spends quite a bit of time with this particular structure that I've shown here. So this is a reproduction of his book. And so this is a beam that is projecting from a vertical wall. And the beam is horizontal to that wall. So it's supported only at one end. And this is known as a cantilever. So he asked questions about this beam. If you put a weight on it, what happens on the unsupported end, and if it's going to fracture, where's it going to fracture? And he correctly surmises it'll be at point AB. And what happens if you use the same amount of material, but it's not as high, right? So you change the thickness, but have it wider or have it longer, make it longer, or maybe you reduce the amount of material and make it longer, or et cetera, et cetera. So he played around with sort of manipulating this mechanical orientation and thinking about what is going on internally in this beam. And this is pretty profound, really. So this is the first, one of the first people to really think about these internal microscopic properties and the relationship then with external shape and size of the structure. What we would now call the morphology of the beam, the shape and the size of that structure. Today we have a more complete understanding of the internal forces at play in a solid that hold it together, and how these internal forces respond to external forces or loads. Before I get into the internal workings of a solid, I want to mention that, when we ask a question such as how strong is this bone, because we have this better understanding of these microscopic forces and their interactions with macroscopic forces, we can be more precise. We can really ask questions such as, how much stress can be applied to this bone before it either bends or breaks. So that's a more precise way of asking the question. So stress is the force that is applied over a given area. So when you're thinking about applying a force to a solid, it matters how that force is applied in terms of how it's spread out and comes into contact with the solid, with the surface of the solid. And there's basically different types of stresses. 3 of them are very basic, and all other stresses are combinations of these 3, and I've illustrated them here. So you can take a solid and you can pull it apart, and that's said to load the solid in tension. Or you can push it together, and that's compressing the solid or loading the solid in compression. Or you can push on it from opposite directions at right angles, and that's known as shear. So if we think about how these forces, these external forces, tension, compression, and shear, are acting on this internal structure, you can imagine your structure that is held together, your solid is held together, the atoms are held together by springs. So the atomic forces behave very much like mechanical forces of a spring behave. So let's just take tension, for example. Let's say you pull the top of this solid upward and the bottom downward. Well, when you initially start pulling and loading this in tension, the springs don't necessarily move. You might add this tension and there's no change in the location of those atoms. But if you add enough stress, if you add enough tension, they will start moving. And then if that stress is released, the atoms will spring right back to their original location. However, if you stretch those springs even farther, they start to get bent. And now when you release the stress, they don't spring back to exactly the same location. They're deformed. So what's really going on there is that the bond between one atom and its neighbors is actually breaking and reforming with different neighbors. So it might go back, but it's not going to necessarily go back to exactly the same shape. And that's true also in compression. So let's say you push down on the top and up on the bottom so that these springs compress. Initially, you might add this compression, this force, over those areas, and the springs are stiff enough that nothing moves. You've added the force, but there's no movement. However, if you add a little bit more force, then they start to move, and a little bit more force, they move even more. And they're kind of linear in their movement during this initial phase when they're starting to be compressed. And then if you turn loose, they spring right back to the original location. So the atoms move right back to the original place. However, if you push too much, you compress those springs until the point that they're sprung and damaged. In other words, the bonds between the neighboring molecules are shifting and changing, and they're forming new bonds with other neighbors. And the same is true in shear. Think of holding the top and the bottom of this cube of molecules, and then sliding the top in one direction and the bottom in the other. So you're causing the molecules to slide past each other. They're not moving to be closer to each other or farther apart in the same orientation as tension and compression. They're sliding. You're sliding or shearing the structures. And the same is true. Initially, you might load it in shear, no movement if the springs are stiff enough, and then they start to move. Turn loose of it, it goes right back to its original orientation. But if you go too far in shear, those springs get damaged, the bonds reform, and now you have a deformed structure. Deformation of a solid in response to an externally applied load is known as strain. There are different types of strain, but there are 2 that are quite important to the way that bone responds to stresses. The first is linear strain, which is the change in length divided by the length of the original structure. So that's a fraction. However, it is often expressed as a percentage, so you simply multiply that number by 100. The second type of strain is called shear strain, And this is a change in angular relationships within the structure, and it is expressed in radians. So linear strain is represented by the Greek letter epsilon, and shear strain by the Greek letter gamma. Now, in this region I was talking about where deformation is completely reversible, the relationship between stress and strain is pretty linear for many materials, including bone. So a little bit of stress, whether it's compression or tension or shear, a little bit of it causes a little bit of deformation. Or a lot of stress will cause quite a lot of deformation. So it's not exactly one-to-one, of course. You have to multiply by some constant, but it is a linear relationship. This is known in, if you're thinking of the mechanical springs, this is Hooke's law for how they work. So as long as you don't spring those springs too much, one way or the other, the molecules or the atoms will snap right back to their position. So in tensile and compressive stress and the linear strains that they produce, this constant is known as the modulus of elasticity. So another way to write that is to say the elasticity is equal to the applied stress divided by the strain that it results in. However, there are a couple of other common terms that are used to describe this constant. So it's also known as Young's elastic modulus and modulus of stiffness. So I'm sorry there's three different terms, but that's just tradition, right? So the constant that relates linear strain to compressive and tensile stresses is known as the modulus of elasticity. It's also called Young's elastic modulus and the modulus of stiffness. When a structure is loaded in shear, lines of the structure that were initially at right angles on a plane surface within the structure change their orientation, and the right angle either becomes obtuse or acute. Shear strain is the measure of the amount of angular change, gamma, represented by gamma, in a right angle lying on this plane of interest. So that's shown here. So just as in linear strain, when in the region where the strain is reversible, so you add shear stress, and when that stress is released, the material goes right back to its original orientation. That linear range, you can simply multiply by a constant in order to get the relationship between the stress and the strain. And this constant is known as the elastic shear modulus, and it is represented by a capital G. It also has another name. It's sometimes called the modulus of rigidity. So the elastic shear modulus or the modulus of rigidity, that's the constant that you multiply in order to relate shear stress to shear strain. There's a third type of strain that is relevant to aquatic animals, particularly those that live at some depth, and that is simply pressure. So strain is force per unit area. That's the same measure as it is at pressure. And if the pressure is applied over 3 dimensions, then there can be a change in volume. And again, if it's linear, if the shape will spring back when the pressure is released, then you can describe the relationship between the pressure and the volume change with a constant, and that constant is known as the bulk modulus and is represented by a K. The relationship between the load applied to a solid, and its deformation can be represented graphically, and that's what's shown here. This is a load deformation curve. So the load is on the y-axis and the deformation is on the x-axis. And this is actually data from a human femur that is being pulled in tension from both ends of the long axis of the bone. So there's an initial region in which you're adding this tension and the bone is deforming a little bit. And that's a pretty linear region. And as I mentioned, initially that bone, when the load is released, will move back to its original shape. So that's the elastic region. But at some point, enough energy is added and enough force is added. You pulled it so far apart, they start breaking these bonds and they start reforming with neighbors. And now when you release the load, it doesn't return to its original shape. So there's damage being done internally in a bone. And you enter this plastic region. And then when even more energy is added and even more tension is generated, more force is added, ultimately that bone is going to break. And that's the ultimate failure point. Now the area under this curve is the amount of energy that bone will absorb before it fails. So the area under the curve to point C is the amount of energy that bone will absorb, or that material will absorb, before it fails. This is the relationship between stress and strain for 3 different materials, metal, glass, and bone, expressed graphically, where stress is on the y-axis, strain is on the x-axis. And if you wanted to compute a modulus, you could do that from the slope of the line, so the rise over the run, when the material's in that linear range. So you can see if there's a greater rise, if it requires more stress for a given amount of strain and a given amount of deformation, then you're going to have a steeper line. And that number, that slope, will be a larger value. So the larger the value, whether you're talking about the modulus of elasticity, if it's something that's loaded in compression or tension, or whether you're talking about the modulus of shear, something that's been loaded in shear, a bigger value means you're working with a stiffer structure. Another thing that's really noteworthy is the huge difference between, well, the slope of the line for metal compared to these other materials, particularly bone. So it's a much stiffer material. And it takes a lot more stress before it finally reaches the yield point and moves into that plastic region where it's deforming and not going back to its original shape. And then that plastic region goes forever compared to glass and bone before ultimate failure is reached. So what that means is that it's more deformable. And it also, you can tell that, in fact, there's a little break in that line because it required so much more stress that it would be awkward to continue the line up on the same axis, right? And so they broke the scale because metal, it requires so much more energy to reach that failure point. So the area under the curve is much greater under metal than it is under bone. Glass is interesting in that it's linear. It's let's say it's loaded in tension. We have this linear behavior, and then it just reaches its failure point. So it really can't be stretched and deformed into a region where it just stays deformed. As soon as you reach that phase, that yield point, it fails. So it's called a brittle structure. And here, from this paper, they point out that this linear region of bone is less linear than for a lot of other materials, and that's because bone is complicated. It's a composite material. So structurally and inside, it's pretty complicated material. These data show some of the complications of this composite material bone. So this is a bone that has been loaded in stress, but the stress has been applied, or excuse me, in tension, but the tension has been applied along different axes. So it has been applied parallel to the long axis of the bone, but also perpendicular to the long axis of the bone and at 30 and 60 degrees. And you can see the stress and strain relationship varies quite a lot depending upon exactly how you're pulling on that bone. So this is known as anisotropic behavior. It's not the material responds differently depending upon how that stress is being applied. The amount of stress a material can take before it reaches the yield point or the ultimate failure point depends on how the stress is applied, which type of stress, which is illustrated here for cortical bone. So the bone can withstand much greater stress when loaded in compression than in tension, and yet greater stress when loaded in tension than in shear. The type of bone also makes a difference. So these gray bars that you can see down at the bottom of the compression and tension bars are the trabecular or the spongy bones. And they're considerably weaker than the cortical bones. And they're not that different. So spongy bone withstands tension about as well as it does compression, which is really pretty interesting. Other biomaterials such as cartilage, tendon, ligaments, they also have different strengths depending upon whether they're loaded in compression, tension, or shear. So let's turn our attention to some more complicated stresses. So we talked about tensile, compressive, and shear stresses, but oftentimes there's a combination being applied, and so the loading is a little more complicated. And two types are particularly important when thinking about animal form and function, and that's loading in a bone by application of a torque so that the bone twists, and that's called torsion, or when the bone is bending. And I want to walk you through an example of torsion applied to a simple rod, a cylindrical structure like this. And the reason I've chosen to start here is that one of the things that is different about both bending and torsion is the distribution of the material makes a big difference. So it becomes really important. So we need to sort of take a look at that. An important concept when objects are loaded in torsion or bending is the bending moment. And this represents the effectiveness of a force in rotating, bending, twisting an object. And it equals a force multiplied by the distance from where the force is applied to cause the rotation, bending, or twisting. So it's easy to understand with this illustration of the wrench turning a bolt. The longer the handle of that wrench, the easier it is for a given force to twist the bolt. So you have the longer the distance, you can have the same force, but the force is more effective at producing that bending moment. So the bending moment equals the force multiplied by that distance. This is a very important concept to grasp, to understand how natural selection has shaped bones for particular functions. I would like to start out with an example of bones loaded in bending and in torsion. This is an illustration of a bird in flight. In panel A, you see that the mass of the bird and the pull of the earth are resulting in a downward force of mg, while the wings are providing an upward force or lift. The center of lift for each wing is illustrated by the upward arrows, and it is important to notice that the downward pull through the center of mass is offset from the upward force of lift, so that there is a moment arm and a torque exerted on the wings. Furthermore, if you look at panel B, you see the feathers displayed along the wing. Each feather has a black dot on it. This is the center of lift being generated by each feather, and this applies another torque to the humerus, the ulna, and other bones of the forelimb. So to understand this, exactly how this torque works, if you hold your arm out horizontally and imagine that it's the wing of a bird, and that you have feathers trailing off the back of the arm, and you look down your arm towards your hand, if you had those feathers there generating lift, what they would tend to do is to twist your arm in a counterclockwise direction. So you would feel a twist or a torque moving your arm in a counterclockwise direction. Now notice in panel C an illustration of the ulna, and it's a hollow bone. Rather counterintuitively, hollow bones are much stronger when loaded in bending and in torsion than solid bones composed of exactly the same amount of material. I find it rather remarkable that Galileo figured this out in the 1600s. So here's a quote from his book. He says, he wrote, "I wish to discuss the strength of hollow solids, which are employed in art and still oftener in nature, in 1,000 operations for the purpose of greatly increasing strength without adding to weight. Examples of these are seen in the bones of birds and in many kinds of reeds, which are light and highly resistant both to bending and breaking. For if a stem of straw which carries a head of wheat heavier than the entire stalk were made up of the same amount of material in solid form, it would offer less resistance to bending and breaking. Men have discovered, therefore, that in order to make lances strong as well as light, they must make them hollow." So I've shown a photograph of the head of wheat with its shaft, and you can see how small that shaft is relative to the head of the seed head. And then below it in panel A is a cross section of that wheat shaft. So you can see it's a ring, right? It's very hollow. And then the bones that I've shown are actually, I think this is so exciting. This is synchrotron data of bones from Archaeopteryx, so one of the first birds that dates back to the Jurassic and is now extinct. And so what these authors did, and they published this in Nature not too long ago, is that they looked at the shapes of these bones and considered the sorts of torques and bending moments that the bones were undergoing, and tried to deduce the flight mode of these first early birds. Galileo points out that the strength of a hollow tube exceeds that of a solid cylinder in the ratio of their diameters, whenever the two are made of the same material and have the same weight and the same length. So why is that? Why is it better to distribute this material in a ring, in a hollow cylinder, than it is to have the material as a solid rod? So there's strength both in terms of bending to consider, and there's strength in terms of torsion. And then, of course, in reality, something like the bird, those bones are undergoing both bending and torsion. Let's start by thinking about what happens to a solid rod that is being twisted. Here, the surface of the rod is marked with a grid before a torque is applied. And the grid lines that run parallel and those that are running circumferentially are crossing at right angles. However, when the rod is twisted, that is, a torque is applied and the rod deforms, the grid lines along the long axis are stretched, and rotated, but the circumferential lines only rotate. So the angles at which they cross are no longer right angles. Remember, the definition of shear strain is a change in the angular relationships, which we clearly have in this situation. So we have shear strain. To gain some insight into the internal shear stresses that this rod is experiencing, I think it helps to think of this rod as being made up of many discs that are rotating about the center of the rod and sliding past one another and generating an internal shear. Now, let's consider the case when the rod is anchored at one end to, say, a wall, and it is sort of projecting out horizontally. So this is a cantilever. And this is very analogous to the humerus of the bird that we just discussed. So the proximal end of that bone is anchored to the body wall, or anchored into the body, and the distal end is receiving a torque from the lift that's being generated by the wings. And the same would be true with the bat wing, or would have been true of a pterosaur wing. So imagine then a plane through this cylinder that runs from A to B and then into the center of the rod. When we twist, when we grab the end of the rod and apply a torque and twist it, what happens is that the end that's anchored to the wall can't move, but the end that's distal can move quite a lot. And so there's a differential amount of strain that is occurring, right? There's more movement distally than there is proximally to that wall. And if we look at the angle that as you move along those discs, it's getting greater and greater and greater. And this angle has a name, and it's a very sensible name. It is hallelujah. It is called the angle of twist. So that is varying from proximal to distal. Okay, to just sum up, there's a shear stress that is varying radially. It is greater at the circumference than it is at the center of the rod. And there's also a non-uniform variation in strain that is varying from proximal to distal. We're going to generate an equation to describe how the shear stress is changing within this end-on view of one of these discs. So I already mentioned that this is varying linearly with the distance from the center of the disc. So it's greatest on the edge and a 0 in the center. So we can look at one little area within the disc and look at the force that's acting on that. So shear stress, of course, is force divided by area. So it's the little teeny force divided by that little teeny area, so that you can therefore get the force, that little incremental force, is going to be equal to the shear stress times that area. And that's acting at the moment P, right? So it's acting through a moment arm. This is the torque, P. So we can write an equation for that little bit of moment, and that is all of those little moments within this disk have to add up to the total torque. So if you integrate from 0 to r, all of those little moments of torque times the radius times that little dA, you're going to end up with the total torque. However, because of that relationship that you see in the center of the slide, that we have a linear relationship between the shear stress and the radius, that's a ratio, that's a constant, that's linear, right? So we can do something sort of tricky, and we can multiply the top and bottom of the right-hand side of that equation by rho. And when you do that, you get this equation. So you've got a ratio of this shear stress, tau, over the radius, multiplied by the radius squared, multiplied by that little element of area. Well, tau over rho is a constant, so you can take that outside of the integral. And then what you have on the right-hand side of that equation is something known as the polar moment of inertia. And that is often represented as J. So this is really important because what this is saying is that the contribution to the resistance to this torque and is disproportionately important on the very edge of the disk. Well, we already knew that. You can see that, but this is a mathematical way to quantify it. So replacing that integral with J, you can rearrange to get an equation for the shear stress as it varies from the center to the radius, or the outer total radius. Let's turn our attention to finding a relationship for the shear strain, gamma, when the rod is loaded in tension. Recall that shear strain is defined by the change in angular relationship of the particles within the structure. So comparing the relationship of those particles in the unloaded to the loaded state. It is an angle, and it's given in radians. So let's think about how the angles of the grid lines on the surface of this rod change when we applied the torque. One of these rectangles formed by the boundaries of two circumferential lines and two longitudinal lines is highlighted in yellow. And this rectangle, CDEF, has right angles. All of the corners are right angles. Once we rotate this, we see that those corners are no longer composed of right angles. So there's been a rotation of those circumferential lines, but there was no movement along the long axis of the rod, whereas the longitudinal lines both rotated and elongated. So the new angle that's formed between E, F, and E prime is the shear strain. So that's the shear strain. And if we map this back onto the whole rod, what we see is this angle, and it's highlighted in pink, this angle, the shear strain, can be related to the amount of twisting that is done through some trigonometry. So what we're interested in is expressing that shear strain, gamma, with respect to the angle of twist, which here is represented as theta, although more generally it's usually phi is usually used as a Greek symbol to represent it. But at any rate, it's the angle of rotation from B to B prime on that end disk. So all you have to do to relate these two is to find that distance B to B prime, both in terms of gamma and in terms of theta. So gamma, that distance is basically when gamma is very, very small, the distance is the tangent of gamma, right? Which is equal to, we're very close to, almost equal to gamma when gamma is very small. So there's not a lot of shear strain. So the tangent of gamma is given by the, basically, there's a right triangle there. It's the rise divided by the run. So the rise is the distance from B to B prime, and the run is the distance from A to B. That is also at the very end disk, if you're doing this for the very last one, that is also equal to the distance b to b prime over L. However, that distance b to b prime is very close to the arc length b to b prime that can be given by simply the radius multiplied by that theta. So r of theta is also b to b prime. So you can substitute that in for the b to b prime, and you get this equation that gamma, the shear strain, is equal to the radius multiplied by that angle of twist divided by the length of the rod. Now note the radius here is the full radius, but this equation would hold if you were looking within that disk. So if the radius was, 1/2 the total radius of the rod, this equation would still hold. Well, we have an equation for shear stress, and we have an equation for shear strain. And we know that within a range that the relationship is going to be linear. So you could take shear strain and multiply it by some constant, and you're going to get the shear stress. And that constant, again, we call the elastic shear modulus, and it is represented by G. So we can simply, since we have an equation for shear stress and shear strain, we can now relate those two using this constant G, and we can rearrange these equations and come up with an equation for an angle of twist that's given by the total torque that's applied, the total length of the rod, this constant, this elastic shear modulus, divided by that shear modulus, and divided by this polar moment of inertia. To sum up, because the polar moment of inertia, the integral that's shown here, describes the resistance to torsional deformation, and it contains a distance squared term. So rho is the distance from the center of the disk out to the radius. Because that term is squared, then the shear stress is proportional to the area, yes, but it's the area multiplied by how far away that area is from the origin. Okay, so that distance is making a nonlinear contribution to this moment of inertia and to the resistance to torsional deformation. So the outer regions, and you can see this by the size of the arrows, the outer regions are more important in resisting this torque than the inner regions. And so one can therefore make bones or the stalks of wheat or lances light and strong by getting rid of the material in the center. It's not doing any good anyway, or it's not doing very much good anyway, and moving that material out into the periphery. So moving it away from the origin of the moment arm where that force is acting. Let's look at how the distribution of material matters in another complex loading regime that is also common in biological systems, and that is when bone, or here it's a beam, is bending. We have a beam supported by 2 points on each end in this example, and the Earth's gravitational field is pulling the beam down. It's sagging in the middle. And when it does this, the top of the beam is loaded in compression. So the fibers in the wood are being pushed together. But the bottom of the beam, those fibers are being pulled apart. So that's loaded in tension. So you've got both compression and tension loading on this one beam. In addition, if you look at the cross-sectional area of this beam, so if you were to think about lots of little disks, lots of sections, cross-sections of this disk, they're trying to slide relative to each other. So there's a shear force also exerted. So there's a bending moment. The beam is sagging and it's bending into a U shape.
but there's also shearing going on. Uh, so the shear stress is downward, that shear force, and the bending moment is, as I mentioned, complicated. So if you look at the arrows in this image, the ones on the bottom, so they're moving longitudinally along the long axis of the beam. The ones on the bottom are moving to the right, but the ones on the top are moving to the left, so they're moving in opposite directions. Because the top section is being compressed and the bottom section is loaded in tension, it's being pulled apart, there has to be a region right in the middle where the wood is not being compressed or loaded in tension. This is called the neutral surface. So here the fibers are not experiencing this bending stress.
So compressive and tensile strain is the change of the length of the fibers within a beam when deformed compared to the original length. And we can find that original length because the length of the fibers in the neutral bending axis don't change. They're not stretched, they're not compressed. And that length is given by, found pretty readily by the fact that the length of an arc is the radius of that arc and multiplied by the angle that it subtends. So the neutral axis, the fibers in the neutral axis running from A to B are found by multiplying the radius of the arc that the beam is bent into by the angle subtended, the length of the portion of that beam. Then if you want to know the length in some other portion of the beam, you can add a little distance to that r and repeat, do the same thing. So the length from C to D is going to be r plus that distance y multiplied by the angle. The strain then is the difference. How much was it stressed? So you can take the new length, subtract the original length, and then divide it by the original length, AB. And if you plug in the values of r theta for AB and r plus y times theta for CD, you get this equation, which then simplifies to just the distance away from the neutral bending axis divided by the radius. So yeah, that gives you the strain. Then we know in the region where Hooke's law applies, and the deformation is not permanent when the stress is released, that the strain is linearly related to the stress by a constant, that elastic modulus, so we can compute the stress. So now we have our two equations for bending strain and bending stress. Recall that the effectiveness of a force at causing rotation, bending, and twisting of an object is the bending moment, represented by the capital letter M. And this is given by the force multiplied by the distance over which the force acts. We know there was an external bending moment applied to this beam, but internally, and that's represented by the large arrow in this illustration, but how is that distributed internally within the beam? To consider that, let's look at a small area represented as dA, located at a distance y away from the neutral bending axis, and think about the force that is acting on that area. You know that the stress is equal to the force per unit area. That's the definition of a stress. So you can compute the force that's acting there. It's simply the stress multiplied by the area. And then the bending moment is that force multiplied by the distance to the neutral bending axis, y. If you sum all those up, or do an integral over the beam, then you'll find the total bending moment. Now we can replace, we just found an equation for the bending stress in terms of the distance away from that neutral bending axis, and we can plug that in to this equation, and we will get an equation where the moment is proportional to Young's elastic modulus divided by the radius, multiplied by the distance to the neutral bending axis squared for that little element dA. Okay, so the distance squared is important here. The farther that element of area is away from the neutral bending axis, the more it is contributing to the bending moment, the more important it is in contributing to that total bending moment. So that's profoundly important in terms of thinking about bone design. Because Young's elastic modulus is a constant and the radius is a constant, those can be taken out of the equation, out of the integral, and what is left in the integral is known as the area moment of inertia and is often represented by the letter I. We can rearrange this equation for the bending moment if we want to find the ratio of the modulus over the radius, so that's m over r, and put that back into the equation for the bending stress. And that gives us what is known as the flexure formula. Okay, so the take-home point here, the really important point here, is that the material that is located farther away from that bending axis makes a disproportionately important contribution to the bending moment. Let me just sum up and review a couple of these major points. You can calculate the second moment of area about a bending axis pretty easily by dividing your shape. It could be any shape, dividing that shape up into very small areas, and then multiplying that small area by the square of the distance that area is away from the axis about which the bending is occurring. So that can be, that doesn't have to be through the centroid. It happens in this illustration. The axis X is moving through the centroid of the shape, but it doesn't have to be. So that's the axis where the bending is occurring. And then it's convention to write the symbol, so I sub x means that this is the second moment of area about the axis X, right? So you could also do the same thing for the area, second moment of area about the axis Y. But this explains why you can have the same amount of material in a structure, let's say a 2x6, and it might sag when supported by two ends when the long face, the wider face, is parallel to the Earth's surface. But if you tilt it so it's on its edge, now it doesn't sag anymore, right? Because even though it's the same amount of wood in the structure, obviously, more of the wood that's resisting that bending moment is distributed farther away from the bending axis when it's tilted on its end. This also explains why I-beams are used so much in construction. So for the same amount of material, if you distribute that farther away from the bending moment, you get a much stiffer and stronger beam than you would. So these numbers are above these beams of the rectangle that's tilted more horizontally and then edge on, and then the I-beam. Those are it's the same amount of material in each one of those shapes, but so the same amount of area, but it's distributed differently, and you can see how much bigger that second moment of area is for the I-beam. For completeness, I want to mention that bending induces also shear stress and shear strain. So I'm not going to go into the equations for shear stress and shear strain for bending. The math is pretty complicated, and there's no sort of punchline where it's really important that you see the effect that the r squared, the distance from the neutral bending axis is. So the math, you can look up the equations. I'm not going to go through them here, but I do want you to have an intuition for what's going on. So imagine that a beam is bending, but imagine that it's composed of layers of, of, of fibers. When it bends, those layers are going to want to slide past each other. So that's where the shear stress is coming from. But of course, they're glued together, so they can't slide. But when there is failure, when you bend and the structure starts failing because of the shear stress, it often fails along one of these horizontal shear planes. It is important to realize that the neutral bending axis can be a function of other skeletal elements, as shown here in this schematic of the calcaneus, or that's the heel bone of an artiodactyl in figure 2. This is a deer, and this is from the work of Dr. John Skedros. So he was actually an undergraduate here at the University of Utah, and he's now an orthopedic surgeon, but he runs a bone research lab over in the VA center. And so what he's illustrated here is that this heel bone is being pulled because of the action of the Achilles tendon and the superficial digital flexor tendon. The dorsal portion of the heel bone is loaded in compression, whereas the ventral portion is loaded in tension. So he's also shown in part B cross sections at several locations. No, at one location, sorry, that's the next slide. At B, cross section, I think it's mid diaphysis, and he's colored the portion of this bone at this location of the cross section in a darker gray, where it's loaded in tension, and a light gray where it's loaded in compression, and then the line that's marked NA is the neutral axis, the neutral bending axis. In figure 2, he's also shown these cross sections, but he's doing an analysis of the microarchitecture of the bone. So not only are these forces and these bending moments affecting the shape of that bone, but it also has an effect internally in terms of the architecture of the bone itself. So you can see in the table that the portion of the bone that is loaded in tension, marked with this black bar, has a different amount or orientation of collagen fibers compared to the portion that's loaded in compression. So collagen is pretty strong in tension, and it's not as strong in compression. So the major point here is just that these load analyses and understanding these stresses in the bone not only help explain the form and function, the gross form of the bone, but also the microscopic anatomy of the bone. Another example of how bone function is interacting with the rest of the musculoskeletal system is seen in the control of stresses in the femoral neck by the gluteus medius muscle. When the muscle is not contracted and a person is standing on the leg, the lateral portion of the neck is loaded in tension while the medial portion is loaded in compression, as shown here by the direction of the arrows. Recall that bone is a lot stronger, considerably stronger when loaded in compression than it is when loaded in tension. However, when the gluteus medius contracts, it causes compression on that lateral neck. So it's going to reduce the risk of fracture if you have a strong gluteus medius muscle. Another example is when a person is skiing, there's a bending moment placed on the bones of the lower limb such that the front part, leaning forward, right, the front part of that bone is loaded in compression, but the back part, the posterior part, is loaded in tension. However, contraction of the gastrocnemius and soleus muscles stiffen the leg and produce compression in that posterior portion of the bone and help protect it. So you can see why injuries are more likely to happen when people get tired, when their muscles are fatigued, or animals too. So, and also if one has poor posture in various ways, so that they're loading bone such that it's weaker. Um, this lecture has focused on the biomechanics of bone, but this type of analysis is appropriate for other building blocks of organisms. For example, the strength of muscle is proportional to the cross-sectional area of the muscle. Well, we know that intuitively, right? If you work out, your bicep gets thicker, doesn't get longer. But the speed at which a muscle contracts is proportional to the length of the muscle. So you can kind of see right there how muscles that have different functions, whether they're important for speed or important for force or combination, are going to be built differently, and they're going to work differently with the skeletal system. I hope this lecture has given you a new perspective to view biological design, so that when you look at structures, you can see them with new insights. I hope it helps you to build a foundation for understanding why animals are built, organisms are built the way they are, and that armed with this new understanding of how forces load bone and the importance of shape for bone to withstand these loads, I wish to turn to the topic of what happens as animals increase in mass, to better appreciate Galileo's insights into scaling relationships.